Hello everyone, today we're going to talk about shifted conics. You already know two equations of conics, which are hyperbolas and ellipses. And let's talk what is going to be like shifted hyperbolas and ellipses. But first, let's go back to a circle. Circle equation is looking like x minus x, well, we had h actually, right? So we have x minus h squared plus y minus k squared equals to radius squared. What is this? This is shifted equation of a circle, right? The center of this circle is going to be h and k. This is h. And the radius is going to be r, right? Well, what is going to happen to ellipse if we apply the same transformation here, ellipse? Well, ellipse is looking like a circle, just a little difference, right? So we can have x minus h squared over a squared plus y minus k squared over b squared equals to 1. Basically, very similar to a circle. The center of the ellipse is going to be shifted to center is going to be at hk. I'm going to consider one example for shifted ellipse. So basically you graph normal ellipse and then take it and shift it indirectly. Place the center of that ellipse at point H and K. So example, x minus 1 squared over 4 plus y minus 5 squared over 9 equals to 1. So this is going to be ellipse shifted to the point of 1, 5, so the center, right? What I'm going to do, guys, I'm going to graph ellipse x squared over 4 plus y squared over 9 equals 1, and then shift it to this position, center. Okay, well, how do we graph it? Remember that number under x is going to define dimension under x, and number under y is going to define dimension under y. So under x we have 4, so it's going to be 2 units here, 2 units here, and 9, the square root is 3, right? That's 3 squared. It's going to be 3 here and 3 here. And that's going to be my ellipse. Well, not a very nice one, but still kind of okay. Oh, sorry, it's supposed to be 2 here. And 3 over here. What should I do with this ellipse now? Well, the center of my ellipse is 0, 0, right? I should place my center now at the point 1, 5. So 1 unit here and 5 units up. Well, basically, guys, I'm supposed to put my center somewhere here. It doesn't look like my picture is going to accommodate it. So what I'm going to do, I'm going to draw a new number line. But now, because I know that my ellipse is supposed to be very, very far up, maybe I'm going to make it like more like x-axis here and y-axis here, and kind of find the center of my ellipse. 1, 2, 3, 4, 5. That's going to be the center, right? 1 unit and 5 units. And now from the center, I'm going to step 3 units up, 3 units down, 3 units down, and 2 units to the left and 2 units to the right. And graph, sorry, I stepped over here, not 2 units, but 3 units. That was a wrong point to do. And graph the ellipse. So that's going to be my ellipse. And sorry, y over here, x over here. So this point is what, 3? And this point is -1. Okay, that's shifted ellipse. What is going to be shifted parabola or hyperbola? Well, same way. X minus h squared over a squared minus y minus k squared over b squared equals 1. So that's a shifted hyperbola with center h and k. Well, let's consider maybe kind of equation. Well, I don't know, for hyperbola, let's consider something like this. X plus 2 squared over 4 plus, not plus, minus, let me make a square better. doesn't look like a normal square. Y minus 3 squared over 4 equals to 1. So where is going to be the center? Center is going to be minus 2, 3. Why? Because it's supposed to be minus h, right? So plus 2, it's actually minus 2. So my h is this minus 2. Now, I'm going to graph first normal hyperbola and then kind of shift the center, okay? So we don't mess with two different operations at the same time. Well, I see that I have the same number under in denominator here. So this is 2 square and also this is 2 square, right? So my rectangle is going to be actually a square. For hyperbolas, it's okay. It's not going to turn hyperbola into a circle. Which way hyperbola is going to be? Well, x squared over 4 minus y squared over 4 equals 1. We understand that if we set up x equals to 0, we have no solution. So we are going to set up y equals to 0, and that's going to give us x centers. Okay. Something like this. That's my original hyperbola. This is 2, and this is 2. Now I'm going to draw a shifted one. The center of my new hyperbola is minus 2, 3. So maybe I'm going to kind of draw a new coordinate plane over here. Because it's shifted down, I'm going to kind of put something, not down, to this side of x-axis. I'm going to put it like this, okay? No, it's actually shifted up. Oh, why do I looked at minus 2, sorry. Computer keeps turning different stuff on which I don't need. So we'll do minus 2, x, minus 2, and 3 as y. And that's going to be the center, which is this one, right? From the center, we are going to draw a fundamental rectangle. In our case, it's a fundamental square with 2 units around, right? And then draw the asymptotes and just kind of copy the hyperbola. Here. And over here. And that's going to be our shifted conic. Okay. Slightly more complicated example of shifted conics. Example 3. 4x squared plus y squared minus 8x plus 4y plus 4 equals to 0. Remember, we had equations like this when we had a shifted circle. That's somebody took a circle and opened the parentheses over there. The same can happen with hyperbola or ellipse. For this one, because it has x squared and y squared and other powers of x and y are first powers, there are no mixed powers, that's going to be a shifted conic. We need to find out which one is it. We can do this only by completing the square. What I'm going to do, guys, I'm going to move all x terms together. 4x squared minus 8x. I'm going to leave little space over here. And then I'm going to put, oh, sorry. This is unnecessary line. I'm going to put y terms plus y squared plus 4y. And let's keep this plus 4 over here. So if I want to complete the square, first I'm going to take this 4 outside of parentheses here. Remember how we complete the square. So we have x squared minus 2x. What is missing to complete the square here? Well, if you take this 2, divide over 2, and then square, you're going to have plus 1, right? Well, remember that we cannot just add 1 over here. We're supposed to also subtract it. For y, we don't have any coefficient in front, so we just kind of look at this. And this is already completed square, actually. That's y plus 2 squared. Well, it's just like y squared plus 2 by 2y and plus 4. 4 is 2 squared, right? Remember the formula. A squared plus, write down the formula for the square. A plus b squared equals a squared plus 2ab plus b squared, right? So we already have this here. Here we just kind of subtracted 1 to not change it. Now, this one is going to make a perfect square of x minus 1, right? Because this is kind of b, and that's what is squared here. B squared is b over here. So what I have 4 x minus 1 squared. And if I distribute this 4 onto this negative 1, I'm going to have minus 4 and plus y plus 2 squared equals to 0. Now, I'm going to move this 4 to the right side. So it's 4x minus 1, moving this one to the right side, plus y plus 2 squared equals to 4. Well, it's almost a conic, but I'll need one here to see if it's ellipse or hyperbola. And I'm going to divide by 4 both sides of this equation. So I have x minus 1 squared plus y plus 2 squared over 4 equals to 1. And now we can kind of tell that this is shifted ellipse. You see? Well, why it's ellipse? Because we do have plus over here. Usually, guys, you can guess that it's an ellipse by looking at x squared and y squared. If both of them are positive or both of them are negative, then it's going to be an ellipse. If one of them is positive, one of them is negative, that's going to be a hyperbola. Okay. Okay. Basically, that's all about hyperbolas. And I just want to maybe talk a little bit about reflection property of ellipse and hyperbola. Okay, reflection points of ellipses and hyperbolas, a little bit of physics. And I know that we just did a shifted ellipse, but if you have a hyperbola, the only difference is going to be that you are going to have a minus here somewhere in front of y. Don't forget to take the coefficient first outside if you do have coefficient. For example, here we didn't have coefficient in front of y, so there is nothing here, right? But we had coefficient in front of x. First, take it outside. Then don't forget to distribute it into what you add arbitrarily to the formula. A little bit about reflection properties. For ellipse, usually ellipses, they do have 2 focal points. And what is going to happen if you put a source of light or a sound in one focal point of the ellipse? The light will go to the wall of the ellipse, reflect, and go through the second focal point. And everything is going to behave like this. All light is going to concentrate in a second focal point. Means that if you stand in the first focal point of some elliptic building and say something like very quietly, whisper something, eventually your sound is going to go around the walls and going to concentrate in a second focal point. If somebody who stands in a second focal point is going to hear your whisper, even if like somebody next to you is not going to hear it. But in a second point, you are going to have a concentrated waves from this focal point. So that's reflecting property of an ellipse. Okay, reflection property of the hyperbola. Remember that hyperbola also have 2 focal points, focal point 1 somewhere here and focal point 2. What happens to hyperbola, how it's going to kind of work with the light? Imagine that hyperbola is kind of a mirror, the mirror which is like this, the mirror like with coverage outside. Then if you have a light which is supposed to come to one of the focal points, like this one, then this light is going to be reflected from this mirror into a second focal point. And well, if you don't have actually a second mirror here, it's going to just concentrate in the focal point. So it's kind of, you have one mirror, which is kind of not really like a flat one. but something like this, that's a mirror, right? And if you put a light which goes to one of the focal points of this mirror, or focal point of the mirror, then it's going to be reflected from that mirror and concentrate in the second focal point. Using some telescopes. I did not explain how parabola is going to work. If you have a parabola is also going to have a focal point, but the light which comes to parabola as a parallel light will concentrate in that focal point. So you can catch lots of parallel light in the center of a parabola. Then you can put a mirror here, a mirror in front of this focal point, and it's going to be reflected to somewhere here behind the parabola, and that's going to work as mirror telescopes. So not all telescopes are made with lenses. Some of them are made with mirrors, and one of examples is to use parabolic mirror to catch light from the stars, right? But right in front of the focal point, put a hyperbolic mirror here, which is going to reflect actually all this light somewhere in a little hole over here. And here we can kind of hold it. Let me draw this. Parabola, hyperbola. And this light will be reflected into the, like a second focal point of the hyperbola. And you can look at this light over here or put a camera. Okay, sorry. That's going to be all about conics.